A very good day to all. Today we are going to have the part 2 of chapter 4, simulation of separation process, and in part 2 we will focus specifically on the rigorous distillation column. So a little bit of the learning outcomes before we go into the content in detail. So upon the completion of this topic, you should be able to first describe the rigorous distillation model, of course. This is in specific RECFRAC. Second, identify the minimum input required for the simulation of distillation process using RECFRAC. Third, you should be able to determine the best operating parameters to achieve the desired product purity using the function of design spec or vary. And the last one is you should be able to estimate the column height and diameter using RECFRAC. So RECFRAC is a rigorous multi-stage separation model, and is actually adopting the solution of stage by stage material balances, energy balances, and thermodynamic equilibrium equation, meaning the composition of the inlet and outlet stream of every stage will be solved using this equation, and these stages will be put in series in RECFRAC. So the distillation unit completes much more rigorous calculation than the shortcut method, the other two methods, and can be used to simulate absorption, stripping, extractive distillation, and azeotropic distillation of solids, liquid, and also gases. So in short, it's actually more versatile than the shortcut method. And this model can be used for highly non-ideal liquid solution or processes with an ongoing chemical reaction, meaning if we are having the reaction and also distillation in a single unit, we call it reactive distillation. We can actually use RECFRAC to simulate such process. Okay. So RECFRAC column, in comparison to the shortcut method, RECFRAC can have multiple feed and also product stream, including pump around streams, and it can simulate the column with different internal like tray, random, or structured packing. While in shortcut method, remember, we can have only one feed and two products. So it is actually restricted in shortcut method. So rigorous method, of course, if a rigorous method can produce more accurate result, of course, the process simulation is much more complicated because the equation adopted is actually much more complicated. So this is the RECFRAC flowsheet connectivity. So I have actually tried to put the important points in the rectangle box. Okay, let's start from the top here, top right. Okay. Top right here, we have vapor distillate. Then we have liquid distillate. Okay, you can choose either one or both, depending on your process requirement. So if you are having total condenser, obviously, all your distillate is being condensed, then you have liquid distillate. Okay. So at the bottom here we have bottom product. Okay. Let's go to the middle part. At the top here we have reflux, and at the bottom we have boil up. So this is a portion from your bottom product that being boiled up to the column using the reboiler. So on your left here, top section, you have the top stage, or this is the condenser heat duty. Okay. Meaning the top stage in the RECFRAC model is always your condenser. Then we have feed stream, and we have bottom stage or reboiler heat duty at the bottom here. Okay. The last stage in the RECFRAC model is always your reboiler. So this bring your attention to the box on your right. Okay. So I have actually put it number of stages versus number of tray. So what you learned in unit op last time is you always mention number of trays. Okay. But when you want to use RecFrac as a model, you have to know what are the differences in between these two. Okay. So as I told you, stage 1 in RecFrac is always condenser, and the last stage in the RecFrac model is always reboiler. In the case of you are having a distillation column with 38 trays, meaning you are having 40 stages. How to get 40 stages is actually a summing up of 38 trays plus 1 reboiler and 1 condenser. So it make up to 40 stages. So you have to remember what is stage, okay? How to define stage and how to define tray. So there are some more RecFrac options. So RecFrac, as it's more versatile, you can use it to simulate absorber, and in order to set up absorber, you have to always not to include condenser and reboiler, right? Then in RecFrac, you can also include the vaporization or Murphy efficiency on either a stage or component basis in the RecFrac efficiency form. So you can also do the design and also rating of the tray and pack column. And if you are having a system with a second liquid phase, meaning you are having two immiscible liquid phase in your process, then you can also use RecFrac to moderate, but you have to choose vapor liquid as the valid phase. Okay. So the last point here is using RecFrac, you are able to generate the reboiler and also condenser heat curve. So let's go through one example. Okay. And example 4.4 here is actually the same case with example 4.1. It's just in example 4.1 we are using shortcut method, and in example 4.4 we are asked to use the RecFrac rigorous model. So we have a vapor stream here containing ethylene and ethane with the composition of 68.5 weight% of ethylene and 31.5 weight% of ethane, and the feed flow rate is 7.3 million pounds per day, and the feed pressure is 350 psig, and you are asked to separate these two components using a distillation process, and the whole column here should operate at 300 psi, and you have to use Spink-Robinson as the thermodynamic model and determine the purity of ethylene and in the top and bottom product. This is question A. And bear in mind you have to determine the purity in weight% as specified here. So B, question B, in the case of let's say if we desired to produce a distillate product with a minimum of 99.96 weight% of ethylene, and the bottom product contains not more than 0.01 weight% of ethylene. So this is our target, and with this you are asked to identify the operating parameters in order to obtain the product with desired purity. So in this case you have to use design spec function that I mentioned before to identify the operating parameters of the column. So let's solve the problem. Okay. As usual, we have to first create the blank simulation, then select component, select property method, and then run to generate properties of all the components. So the first step here is actually exactly the same with the one in example 4.1, so I will skip this. So let's shift to the simulation tab. Once you have all the properties generated with the status of results available, then once you are here, of course, you'll be led to a blank page for you to construct your flow sheet. Okay. So in the flow sheet, as usual, you have to put in the block. Okay. The block here, obviously, we have to go to column and select refract. If you are having a typical configuration, you can just choose the first one. So the other option here is you are having a special requirement. Then you can opt the other choices here. Okay? But typically we use the first icon here. So you just put the block. So once you put the block, then you have to, obviously you have to connect the block with the stream, and then you may want to rename your block. So like here I have actually renamed the block as T101. Okay, so I have the feed stream here as 1, the distillate is S2, and the bottom product is S3. Okay. So one point here I would like to draw your attention, and it is about your distillate. Okay, so in the question is given that it's a total condenser. So if it's total condenser, meaning your distillate is actually in liquid phase. Okay. So when you want to connect your distillate stream, you have to bear this in mind. You have to put it after the condenser. There's an option for you after condenser. Then you have to connect the stream here. Okay, to indicate that this is a liquid distillate. Okay. Of course, there are 2 more options. That 2 more options, one is for vapor, the one up there is for vapor. The one at the side is actually for the second liquid phase. Okay. Most of the case is in liquid form, your distillate, but yeah, there are also possibilities. It's a mixture of vapor and liquid, or it is totally in vapor form. So this is very important to avoid the problems in the subsequent steps later on. So if you have put it wrongly, then you may have difficulty to complete the information in the subsequent steps. Okay? So put this in mind, and this is very, very important. So once you have constructed the flow sheet, then you have to click next. Just click next. Okay. Then you will be guided to a page for you to put in your feed information. Okay. So what you have here is you have to choose pressure and vapor fraction, because temperature is not given, but you know that is actually a vapor phase feed stream. So pressure 350 psig, and the vapor fraction is 1, and the mass flow rate is also given, and mass fraction just include accordingly. So we have done the feed information. Then the next step, just click next if you don't know which page to go. Then you'll be guided to a page for you to put in your block information. So this is under the setup page under T101. Okay. So the first page that you need to fill up is configuration. So the parameters like number of stages, reflux ratio, and also distillate to feed ratio, you have to get it from the simulation results of your DSTWU example in example 4.1. So this information, the one on your left, I have actually extracted this from the simulation using the DSTWU. As I mentioned to you before, the simulation result of the shortcut method is important for you to proceed further in the rigorous method. So this is how we extract the information. So we have the actual number of stages is 63, okay, and reflux ratio, distillate to feed ratio, and the condenser here is total condenser. Okay. Total condenser meaning your distillate is totally in liquid form. Bear this in mind. Okay. This must be matching with your flow sheet just now. Okay. If you put total, then your distillate stream must be connected to the liquid distillate option. Okay. Remember this. So the rest, I think you can just leave it. Okay, use the default setting will do. Then the next page here is for you to put in your stream information. Okay, stream information still under the input page. So we have stream information here. Only the feed stage we need to put in. Again, feed stage you have to extract from the simulation results using the STWU. Okay. The bottom part here is for the product streams. So this is by default. If you are having 63 stages, then the first stage is for your S2, and the last stage 63 is for your S3, for your bottom product. S2 is your distillate product. So next here is here we are almost done. For the block information, we have the last page here. Pressure. Okay, the pressure sheet here is for you to put in your pressure. Here you have the condenser pressure, so you can put in the condenser pressure, and with the assumption of no pressure drop across the column. So this is 300 psi, okay, or 300 psia is the same. Okay. And once you have done this, I think all turn to blue. You have to put it on every page. Then you can actually click the run simulation button to get the simulation results. But if you don't know which page to go, just click next, and you'll be guided to a message asking you to run the simulation, because all the required input is already in. Okay. So once you have run the simulation, then you have the results page. You can go to, still under the block, under block T101, you have the results page. Okay. So this is the results with the status of results available with no error, no warning. Okay. So for sure you don't need to worry to extract the information, because this is a green button for you to extract the information. If it's with error or warning, then you have to check the message under the control panel. Then you have to troubleshoot accordingly, and you have to judge whether you can extract the information or extract the simulation results safely. Okay. So here under the results page, you can have like the condenser duty, reboiler duty, okay, and also the reflux ratio, and also the reboil ratio. If I'm not mistaken, you can check later on. And if we move to stream result, so there's another page for you to check the stream result. So this is a page. You can have a mass fraction here. So this is actually the answer for question A. You need to check the ethylene composition in the top product. So this is the top product here, and you have to check the ethylene composition in the bottom product. 99.11 weight% ethylene in the top product, and 1.13 weight% of ethylene in the bottom product. Right. So next, proceed to question B. So as I mentioned earlier, question B, you need to use design spec vary function. You need to set the target, and then you have to vary the operating parameters accordingly, so that you can get the product with desired purity. Okay. So here, under the block T101, you will have a function of design spec and also vary. So this is a little bit different from the design spec that we learned before, okay, in terms of configuration. Okay. before this, the design spec is actually under the flow sheeting option, if you remember. So in this case, whenever you have RecFrac model, you can actually use the design spec under the block itself. It is easier in comparison to the design spec under the flow sheeting option. But if you accidentally opt the one in flow sheeting option, doesn't matter, we still can proceed. It's just the configuration for you to put in the input is a little bit different. But my advice is always use the design spec and vary function that are available under the block RecFrac. Okay? So what you need to do is go to design spec and you have to click new in order to generate design spec 1 and 2. Here we have two target, right? The targeted purity for the distillate and also bottom product. We have two target, that's why we set two here, two design spec. So let's put in the design spec number 1, target number 1. So target number 1 is the mass purity of ethylene in the top product must be at least 99.96 weight%. In fraction, it is 0.9996. Okay? So you have to choose mass purity. Obviously, this is mass because weight%, and you have to put in fraction basis. So this is the design spec 1, specification. Let's move. So under the component tab, you have to tell the system what are the components that we are targeted for. So we are targeted ethylene. Okay. So originally you have a list here on your left. So you have to shift ethylene as to the right hand side as your targeted component. Okay. So this is your targeted component. Under the base component here you have to select all the component to the right hand side. Originally all the list is here. You just need to click the button here, the second button, then all the component will be shifted to the right hand side. Why all the component? Because based on the equation of mass purity of ethylene, if you refer to the equation here, is equals to mass of ethylene over total mass of top product. Okay, meaning the section on your left is actually for the targeted component, the component ethylene here, and the section on your right is to include the basis. That means the denominator in the equation. It is actually all component in the top product. That's why we select all component here. So this is the justification to select all the components as the base component. So moving forward, we have the third tab here for specification 1. Okay. So you have to tell the system our target is for which stream. So this is for the distillate. Okay, distillate, because it is the ethylene purity in the distillate. So we have to choose S2 and shift S2 to the right. Okay. So once you have this done, then you have to proceed to do the same for the design spec 2. Okay, design spec 2. Design spec 2 is about the mass purity of ethylene in the bottom product. It must be less than 0.01 weight%. So in fraction, this is the one in fraction, 0.0001. Okay. Just put it accordingly. Just follow the procedure as a design spec. You have to fill up the 3 tabs here. So once you have done this, still incomplete because design spec and vary must come in pair. So if you have 2 design spec, make sure you have 2 vary. Okay? Now we move to vary. As usual, you have to click new to create 2 vary. So the first vary here is first vary here is I have actually asked you to vary reflux ratio as the first vary, and second vary is a distillate to feed ratio. You can actually swap it, doesn't matter. Okay. Let's say if you wish to have a distillate to feed ratio as your vary 1 and reflux ratio as vary 2, doesn't matter, you can swap it. How should we make decision on which parameter we should vary? Okay. So typically we will refer to the configuration page of the RECFRAC. So this is the configuration page. So under this page, the parameters that we have is reflux ratio and distillate to feed ratio. So obviously we are going to vary these two. Okay, and of course there are cases also you can vary the number of stages. But before you vary the number of stages, you should vary these two operating condition. Okay, so let's put it in. We have the vary 1 reflux ratio. And the range that we ask the system to vary is from 1 to 10. Okay? And this range should encompass the value that we have put in to the configuration page. So the one here is 4.156, okay, the reflux ratio here. So make sure the range that you suggest, including the value that you set in the configuration. Okay? You cannot set like 0.1 to 1, cannot, because you are not allowed to simulate later on, because this is the value that you put in your configuration is actually outside the range. Okay. So we have this done. Then we go to the second vary. Second vary is distillate to feed ratio. Bear this in mind, whenever you have distillate to feed ratio, this is actually a fraction. So a fraction meaning must be in between 0 and 1, but you cannot put 0 and 1 because the simulation will turn up with error. You have to put a minimum number and a number which is very close to 1. Okay, so for me, I will always put 0.01 to 0.99. Okay. So I think we have all the design spec done. Okay, then you just run the simulation, and if you don't know which page to go, just click next. Then you'll be guided to run the simulation. And this is the results. If you go to design spec, and there's a results for you, just click results. So after the design spec execution, you are able to achieve the desired purity. Okay, this is a desired purity, calculated value. This is a revised purity after you adopt the new parameters. So what are these parameters? Okay. So you can go to vary, again under results, you can have this calculated value. Meaning if we operate the column with the reflux ratio of 8.13 and the distillate to feed ratio of 0.7, we are able to get the desired purity. Right? And these are actually the answer for question B. So in question B, you are asked to identify the parameters to get the desired purity. So the parameters would be reflux ratio is equals to 8.129 and the distillate to feed ratio is equals to 0.7. Okay. So other than this, you can also check the result stream under the block. So now, this is your targeted purity. We have successfully obtained the product with the desired purity. Okay. Top product, ethylene in the top product, ethylene in the bottom product. This is the mass fraction. So to answer question B just now, yeah, you have to specify the identified operating parameters, and yeah, you have to answer that the separation process is feasible because we are able to separate the ethylene to the desired purity using the distillation column. So this should be the answer for your question B. Okay. Of course, here you may be wondering, we have not changed the parameters in the configuration. We only use the design spec. function. Once the design spec function is executed, the composition of your stream will be revised accordingly, even though you don't change the parameters in the configuration sheet. So you have to bear this in mind as well. Okay. So we have done session 1 for rigorous method. We'll proceed to session 2 later on for another example, and also for the conclusion for the rigorous method. Thank you very much.